All right, let's see if I can pull off this idea of using this composition of our linear transformations to sort of define an inverse matrix. So we're going to go ahead and work through this problem using those transformations on our standard basis vectors because TBL convinced me that that was a good thing to do. And then we could also talk about matrix multiplication right after. So let's look at this particular setup. We have a standard matrix. It's a linear transformation taking us from R2 to R2. We can see that it's injective. We can look at those two different columns and see that they are linearly independent. One is on a multiple of another. So I am good. I've definitely got 1 to 1. And then because my two columns are linearly independent, that means I'm going to have the ability to span all of R2. So this is also on 2. So I have a bijection, which is what I need to be able to go backwards, because if I had stuff mapping to a kernel, right, if I had a kernel mapping to the 0 vector, I'm not going to be able to get back that information in that second step, right? Because our goal here is to go from some vector in R2 using our transformation to our image, and then to use that S, right, some new transformation that we're going to define, this inverse transformation, to go back to our original vector. The question is, can we do that? So let's look at T of our first standard basis vector in R1. We know that that's just going to be the first column of my standard matrix. I could do the same thing here, 0, 1. It's going to be the second column of my standard matrix. I'm going to go ahead and turn off my camera because my husband's about to get home from running. You don't need to see that. Anyway, so we got those two. Now, if you think about this, we are currently in this section, right? We have our images, and we want to see if we can map those back to our original vectors. And this is where things start to get a little bit suspect, and it's taken me a long time to sort of wrap my head around what I'm doing. But I'm going to take this new non-standard basis, which makes me deeply upset, and I'd like to say it maps back to our standard basis, right? So these two things have to map back. Okay. Now here's where things get weird. Because we want to define this in terms of the standard basis and not in terms of some weird basis that is really hard for us to think in. And so we have to realize that when we did things like figure out what S or what a map was from a vector, we could just rewrite this as 2 times our vector, right? So whatever x1, y1 we had, plus 5 times some other vector, x2, y2. Right, so our goal here, if I knew what the standard basis was, if I had that, right, and let's say x1, y1 is that standard basis, I don't know, I would do 2 of it plus 5 of it, and that would hopefully result in my image. It's a little weird to be going backwards, but the nice thing here is we get a system of equations. We have 2x1 plus 5x2 is equal to 1, 2y1 plus 5y2 is equal to 0. And right now we're going, oh crap, 2 equations, 4 unknowns, not good enough, but we can see we have another vector, right? We have another piece of information here. So you have -1 times our x1, y1 minus 3 times our x2, y2 is equal to 0, 1. And there's our second set of equations. -x1 minus 3x2 is equal to 0. And -y1 minus 3y2 is equal to 1. So we should be able to use those together. Ugh, I did not give myself enough space to solve for what those transformations would need to be for 1 and 0, right? In theory, what I'm doing here is breaking this up and saying, okay, we're doing S of 2 times, S of 2 times the vector, standard basis vector, plus 5 times our standard basis vector, right? And so I am saying, okay, 2 of S of 1, 0, what is that, right? Like I'm trying to figure out what this thing is. That's my x1, y1, right? That's the goal. Okay, so let's go ahead. I guess I don't have much space here because I can't scroll. But I will I'm going to multiply that second equation by a -2. I'm just going to go ahead and do this by hand. It's small, it's short, it's cute. -2x1 minus 6x2 is equal to 0. Negative x2 is equal to 1. So we've got one of our things that we need. Let's go ahead and do y1 at the same time. 2y1 plus 5x, I'm reading 5y2 is equal to 0, and then negative 2y1 minus 6y2 is equal to 2. I said 6 and I wrote 2. Insanity. There you go. So we get negative y2 is equal to 2. So we've got our x2 and our y2, right? We've got this second thing I didn't bother to find. We now know that s of 0, 1 is equal to negative 1, negative 2. We've got the second column in its transformation matrix, right? We've got this matrix now that we can say, okay, B, I don't know all of it, but I do know there's going to be a negative 1 and a negative 2. And then I could go ahead and figure out the x1s and y1s. Not bad, right? Now that I have part of it, yes, I should be able to do that easily. Let me go ahead and use blue. So we've got 2 times my negative, oops, we don't have that one yet. 2x1 is equal, plus, it's minus 5. That's good. I'll be minus 5 is equal to 1. 2x1 is equal to 6. So it looks like that's 3. And we end up here with same business right here. 2y1 minus 10 is equal to 0. We move that over. It looks like we get y1 is equal to 5. All right. So in theory, this should allow us to move back and forth. So if we wanted to test this, I have to add another page. I can't not. Page, insert. Oh, this is going well. Come on. Let's do 3 pages after, I don't know what page I'm on. Let's hope that's right. Okay, let's see. Yes, perfect. Okay, so let's test this out with just, let's use just an actual number, like an actual vector. So let's just say, let's look at the vector 1, 2, and I want to take the first transformation of this. All right, so we know, right, that this would be 1 times that first column vector in my standard matrix, plus 2 times my second vector in my standard matrix, which is, oh, nice, 0 and negative 1. Cute. Gorgeous. Now, if I do S of this, what should happen, I'm crossing my fingers because I decided to do something real freaking weird. This should go back to 1, 2, right? I should end up back at the matrix I started with. Now, we have our B matrix right here. So I know I need 0 of, oh, look at her, 3, 5. I chose a really silly vector now that I look at my B matrix. And I need negative 1 of negative 1, negative 2. And sure enough, I am back at 1, 2. Now, one vector doing this is not a proof. We know that. So we could go forth and actually try this with an XY. But we have other ways to think about this as well. And that's really where we're sort of heading, is this idea of an inverse matrix. Because if we called this B, we're going to end up labeling this thing as A inverse. The purpose of this is that we know we can represent that linear transformation, that composition, as matrix multiplication, right? The very first thing we would have had was our A matrix, 2, negative 1, 5, negative 3. We did the B matrix second, so that should be multiplication on the left side, because you know the order matters for multiplication. And if we do this matrix multiplication, what should happen, right, is it should give me a transformation that doesn't change anything. And if my transformation doesn't change anything, right, that should mean that my S of t, this transformation thing, should have taken a standard basis vector and mapped it right back to the standard basis, right? The only way we could do that is if my columns are the standard basis columns, right, of that standard matrix. This has to equal 1, 0, 0, 1. It has to equal that identity matrix we've seen before. So this is the idea of an identity matrix. So let's, not an inverse matrix. So let's go ahead. Let me clear. Bring over the Desmos matrix calculator so we can just have it do the matrix multiplication and test some other things. So let's, so slow. Come on, we can get smaller. There we go. Let's go ahead and define our matrix A. That was our 2, 5, -1, -3. Boop. Let's go ahead and just go ahead and define our matrix B. We said that was 3, -1, 5, -2. Let's confirm that if I do A times B, I get the identity matrix. Let's explore and see what happens if I do B times A. Turns out this is fine, and that makes sense if we think about our bijection, right? But okay, cool. And here's the lovely thing is that all of this work, we didn't have to go through all the rigmarole I just made us do with those standard basis vectors and solving this gross system of equations, because we could have just done A inverse, and it would have told us what that A inverse was. So we're going to talk about how to find that inverse matrix, not using technology, and sort of what we can do with it. But this is that first idea of like tying everything together, right? Like if we're really talking about this, we can still talk about it as a standard matrix of a linear transformation. We can still note that the only way that this is gonna have an inverse is if that original transformation that we're trying to invert was a bijection or was an isomorphism. So we need that, which means that we could check, of course, spanning and linear independence, all the things we've been checking before, looking for our number of pivots, matching our number of rows and columns. But yeah, all of these things sort of tying together makes it a lot easier to understand like what it is we can do with this later in the course.